Hello, YouTubers and my students. This is Dave out in Western Pennsylvania, USA. And here in this experiment, I'm going to show you the Beyond Labs' virtual organic chemistry. And we're going to look at H.C. Brown's Nobel Prize winning Hydroboration-Oxidation reaction. And I will be teaching Organic Chemistry Lab 1 this summer from my school via remote because of the pandemic. And I know that with this program, the use of SDBS structural database online, Google patents, the electronic journals, ChemDraw, I have enough that when the students go on to Organic 2 Lab, they will be able to go into the Organic Lab 2 Lab, the conventional lab, feeling quite comfortable. In the future, I will use this virtual organic lab in a so-called hybrid scenario coupled to the conventional lab. And I will even record some short videos that I will show in lecture for each chapter. For example, hydroboration-oxidation. I may call this up and show them that, the students. Okay, let's get started. What we'll do is collect, incidentally, the program is $25 a year for an annual license fee for students in the United States. Other countries, you'd have to contact the software manufacturer, but $25 a year is extremely reasonable for this program. And the tech support is excellent. Okay, so this will open in a minute. And we're going to select hydroboration. And we have a choice of reactants. And I am going to pick the methyl cyclohexene. I'm going to double click. You can try the syringe. I have much better luck with a double click. See how it's in the round bottom? And we'll add ether as a nonpolar solvent. So we have both there. Then we bring the round bottom over to the stir plate. We're going to add the BH3. Make sure it's there. Yep, BH3, THF. Then I'm going to hook up a heating mantle. I'm going to click on a reflux condenser, and we need nitrogen gas. And we'll be ready to start. Now, let's do a TLC first of the pot. And you can see that's where we're at. And we can save that. And then you can click OK. And it'll be in the lab notebook. The TLC will be there. And normally I would have students put their name, the date, the reaction they're doing, the purpose of the reaction. For example, they're investigating hydroboration-oxidation, which is proceeding by anti-Markovnikov addition, and observations, conclusions. If they made a mistake, why did they make a mistake, retrace steps, etc. But I'll X out the lab book now. If you're doing a reaction at lower temperature, you can use ice. You can stir at room temperature, or you can apply heat, which I'm going to do here. Okay, let's get started. Start stirring. Note the lab, the time in the lab. It's 8:20. Now that will change. And you can speed it up if you want, but do that very cautiously, because if you go at too fast a rate, the glassware could explode. And they're using specific rate constants from literature examples to establish some of their rates. Now, let me just do another TLC. And we can see there's just a, small amount of product forming on the right. There's your starting material. And I'm going to now, I won't save that. I'm now going to jump ahead an hour. Now, you watch that blackboard. You see how you have one methyl cyclohexene reactant, diethyl ether solvent, the borane and THF, and already product is forming trans-2-methyl cyclohexanol. Do you see that product? Trans, the methyl and the OH are trans because it involves syn addition anti-Markovnikov and boric acid byproduct, but it's still reacting. Now watch what I'm going to do. I'm going to go up an hour, and I'll try it again. Still there. It's almost gone, but it's still there. Let me go up 10 minutes. Still there. I'll go up 10 minutes. Let's try. And boy, just a trace. Another 10. Another 10. And you can let this run for a longer period of time. TLC. The reaction's done. Starting material is gone. Product's there. I'll save it. Okay. Look at the blackboard. Solvent, product, boric acid. Now we have to do a workup. We have boric acid, so let's throw it in with aqueous base. Watch, click on the SEP funnel. Then what you have in there right now are the product mixture. Now let's put aqueous base, top layer, the target molecule, trans-2-methylcyclohexanol, and solvent. Lower layer is boric acid and water. Now, what we're going to do, because it's a volatile solvent, we're going to rotovap it. So what we're going to do is we're going to take this right over to, let's say, the evaporating dish. The ether will be gone. We don't have to distill the product, and it's in there. Now, would that be a solid? Well, let's see. Let's take a melting point and see if we get anywhere with that. If you don't get lighting up, then it's not a solid. Oh, wait a minute. Let's see. Nope. Now, of course, I would have my students look up the melting point of the product. That goes without saying. They would know and anticipate. No, there's no, that's a liquid in there. We evaporated it in the hood, I hope. You wouldn't want that done on the benchtop. You'd be filling it with diethyl ether and filling your lungs with it. I had my tonsils out with diethyl ether in the 1950s. I'm 67 in June. It was fashionable then. Okay, what can we do at this point? Well, you have a pure product. We can do an FTIR. There's your alcohol. And use the SDBS online database so you can actually get the infrared and compare it. You can save it and then okay. Let's look at the hydrogen NMR, proton NMR. Got to line it up just right. You got to be patient. Maybe they don't have the NMR for that. You'd have to look it up. Let's try C13. Nope, they don't have it. So you'd have to look those up. What about mass spec? There's the mass spec. Molecular ion. You got a base peak. Let's see what it's at. 57.095. That's the base peak. The molecular ion is 114. And very interesting. Very interesting. I'll click save. And then OK. And no, they don't have the NMR for this one. Nope, it's not there. So it's a very interesting program. It really is. I like it. I find it very entertaining. You know, I'm a chemistry professor, organic chemistry, but I find it fascinating. My PhD advisor when I was in school would have loved this. He would have really loved it. And his first student was D.J. Cram, who later won a Nobel Prize in chemistry. Professor Cram spent most of his career at UCLA. Okay, well, that'll do it here. And I hope you enjoy the video. And this, if you decide to get it, look at the various videos I'm uploading, and that will really help you to get down to business, hopefully as fast as possible. You take care. Oh, and this is how you exit. If you want to do another experiment, you just click on this. Clear Lab. If you want to check your notebook, and you can download it and save it at desktop or on a thumb drive, and refresh your memory, recall it. You might even send that to your advisor if you're a student as a Word doc attachment or what have you. I'll X that out. And yeah, new experiment. We'll wipe everything clean and then you're good to go. Make sure you write the time down, how long it took for the reaction to take place. You may want to run one fast, or you may want to let one go at room temperature or with an ice bath or heating it and see how long the reaction takes. And now to exit, click on exit. Click on exit. And I'm not going to save the notebook, so I'll click OK. Then finally, organic chem, higher ed. You'll X out by up here, clicking on this. You also have chemistry, biology, physics, physical science. I can't comment on any of them. I looked at the general chem. I thought there were some very, very good things there. But as for the biology or the physics or something, you'd have to have one of your professors look at that and discuss it with you. Okay, bye for now.